Welcome to the Excellence in Training Academy, where trainers come to grow at excellenceинtrainingacademy.com. I'm very pleased to have with us this week Dr. Geoffrey Desmoulin. Geoffrey is the principal at GTD Scientific, Inc. GTD offers biomechanical consulting services on behalf of clients throughout North America as well as abroad. Focus practice areas include injury biomechanics, incident reconstruction, and physical testing with a subspecialty in the science of violence. GTD has been retained in significant complex injury litigation cases involving municipal police department use of force, violent encounters, and Taser International, to name just a few examples. Furthermore, landmark testing and shooting reconstruction methodology developed by Dr. Desmoulin was recently upheld as reliable and admissible by the U.S. Federal District Court for the Ninth District of California. In addition, Geoffrey was selected from an international pool of applicants to be the science and engineering host for Viacom Network's hit television show Deadliest Warrior. In his high-profile position, he assessed engineering aspects, injury potential, and overall battlefield effectiveness of weapons used by warriors throughout history. The series filmed 33 episodes and highlighted 64 warriors. Deadliest Warrior continues to air throughout the world in over 16 countries, 32 different languages, and is available in over 96 million homes in the United States alone. So, Jeff, welcome to the Excellence in Training Academy.
Thank you, Brian, for having me.
Now, what you do is pretty unique in bringing the world of science into some of these investigations, and I know you, through your company, do far more than just get involved in use of force investigations, but that'll be kind of the focus. Now, what we didn't talk about in the bio is you have a black belt in karate, you have a bachelor's degree in kinesiology, you got a master of science in kinesiology specialized in biomechanics, and then biomedical engineering master's degree specializing in injury biomechanics, and then earned your doctorate in mechanical engineering, again specializing in biomechanics. What was it that got you interested in this field of biomechanics and biomedical engineering?
Yeah, we're going back a ways, Brian, but I can tell you it was my time at the fire department. I was a firefighter at the Canmore Emergency Services, and what I loved about that job was I could combine being an emergency medical technician and learning about different types of injuries and experiencing, firsthand what certain incidents will do to the human body. And combine that with engineering principles such as heat transfer and pump pressures and things of that nature. And so that's really where it started. And I was 23 years old as a firefighter there, and so I was quite young. And circumstances had it that I couldn't continue. And so, but the interest of combining engineering principles and the quantitative power of the engineer, and with the interest of the human body in health and in injury, stayed with me. And so I started looking around at what programs, kind of bridge this gap between these two disciplines. And it turns out biomechanics was it. And so the program that had the most biomechanics in it was kinesiology. So I started as a kinesiologist, understanding human movement, the human body and health and disease, and of course, a bunch of biomechanics classes. But then as I progressed, I understood that, kinesiology is a little bit more on the life sciences side than it is on the engineering side. And some of the people that I was bumping into that I felt were really good in combining those two disciplines tended to come from an engineering background. And that's when I said, okay, well, I've got to go shore that up. So I ended up studying at the source at Wayne State University in Detroit, Michigan, where biomechanics, or I should say injury biomechanics, actually started probably about 75 years ago, where the emergency physician on campus literally took a stroll over to engineering. And he said, sat down with the chair of the department, and he said, you know what, we really need to come up with something to prevent all these injuries that I'm seeing in the ER with respect to car crashes. And hence, injury biomechanics was born. And so I went there to study and ended up with a master's degree in injury biomechanics, but I wanted to take it even further with the hard engineering skills. And so I ended up doing a PhD in mechanical engineering to kind of round myself off, if you will, and kind of really truly understand both disciplines. Because to me, in my humble opinion, it's really a mastery of both disciplines creates a new discipline. And I could talk forever on that, but that's really how it all started, Brian.
Excellent, and that's such an interesting path. And I think a lot of times when we think about bringing science into force investigations, we think about behavioral sciences and behavioral psychology and human factors. But what you do is different. Can you talk about how you approach this differently, perhaps, than what we would historically have thought about from bringing science into use of force investigations?
Yeah, Brian, it's such a great question because I think force science and Bill Lewinsky have changed the landscape. They were pioneers on bringing science to the forefront of use of force investigations. But having said that, and even coined the term force science, but having said that, Dr. Lewinsky is a human factors person. He's a behavioral scientist. And so the focus there has been on human factors, reaction times, and human behavior in deadly force encounters. What we do is we say, okay, that's awesome. We're not behavioral scientists, and so we'll get outside of the brain of the officer, definitely look at observable behavior, but really focus on the loads involved, okay? And so because typically when we get pulled in, there's some sort of injury that occurs. There's been a use of force, and so it's either somebody's deceased or somebody gets seriously injured, and that's why it becomes an investigative, interest. And so when you can characterize the loads that were involved, you really get a better understanding, at least from the engineer's perspective. And so we tend to look at any type of injury that was incurred during a particular contact as a source of independent information. That's a very objective thing that happened, and it details contact between a person and an object, or a person and a surface, or between two people very, very well. And if you can detail the location of the load, the magnitude of the load, and the direction of the load that caused that injury, I believe you have a much better understanding of what actually occurred. And so as far as reconstruction's concerned, that to me is an extremely valuable skill set, and one that I believe makes us different.
Excellent explanation. And something that I saw that in one of the articles about you is you said that we look through the eyes of an engineer at the forces applied to the body and how those forces result in injury. And so it seems to me that that's the piece that a lot of times was missing is what you take is, as you said, you look at the injury as a source of independent information, and then you work backwards to determine what likely occurred or most probably occurred, looking at the location of load, magnitude, and direction of load to determine how those injuries occurred. Is that accurate?
That is very accurate. And let me just expand on that a little bit, Brian. If we look at it as a spectrum, for example, if injury causation is so important in use of force investigations as we believe it is, have a look at the background and training of the average physician that gets involved. Their expertise is in detailing and understanding the diagnosis in order to move forward in time and increase the prognosis. So treat the injury and increase the long-term health of the individual. If it's a medical examiner, my thought process then is to understand the cause of death. So if it's a gunshot wound, for example, we know that many gunshot wounds are not lethal, but often it's the medical examiner's job to determine which one is. But now we're really detailing wound path, the organs that it went through, et cetera, et cetera. And even though things like contusions and abrasions will be detailed or explained, the understanding of how they occurred with respect to the incident is often left untapped. And then you think of it the other side of the spectrum, the pure mechanical engineer, for example. And there's lots of mechanical engineers out there that will tell you they're biomechanists. But I caution you to move in that direction, because there's a reason biomechanics is called biomechanics, is because you're taking life sciences information or you're taking expertise on a biological system and applying mechanical engineering to it. And so it's not just a pure mechanical engineering problem. And the types of pure mechanical engineering problems that they deal with are, say, structural analysis, if you will. You look at, CAD drawings and design aspects of physical structures, like things that I mentioned before, like heat transfer and pump pressures required, an engine to move a certain volume of water. Like, these are the things they do very, very well, and that's a very important skill set. But when you apply that to a biological system, you have to be aware of the nuances of that biological system in order to determine the injury causation. And so it's really understanding the diagnosis the physician has given, or truly understanding the medical examiner's report, and then working backwards in time using the tools of the mechanical engineer to determine the load location, load direction, load magnitude to cause that injury. And then all of a sudden, doors will open where they were previously closed, or even never even thought to have existed.
Excellent explanation, and I think so often we either have kind of that psychological framework or a biological framework or the engineering, but to combine the biological nuances with the mechanical engineering is really very fascinating. Now, just to give people an understanding of kind of how this works, there's a couple of cases I wanted to have you talk about. One was a shooting case where there's a single officer and a subject involved in a struggle. The officer fires 2 shots. Subject dies as a result of that. And of course, as always, now afterwards, the officer handcuffed the subject as they're taught to do, and then applied attempted CPR. Now the allegations were that the officer shot the handcuffed subject, so shot somebody who wasn't a threat to him. And so can you talk about that, where you basically what you have is the officer statement, and then you have the physical evidence from the injuries to the subject. And can you talk, first of all, about how you use that officer statement as a hypothesis and applied the scientific method to work backwards to attempt to disprove that, which is how, I think, very differently than we normally think. We're normally trying to prove something, and you're using that scientific method to attempt to disprove it. Can you talk about that first?
Sure, Brian. Basically, it's just scientific methodology. So let's talk about that first. The scientific method is such that you have an idea around how something should behave. And so we call that a hypothesis. And so in science, then, you test against that hypothesis to try to disprove it. And if you can't reject it, then you end up accepting it. And that's kind of the four steps of the scientific process. And so in a situation like the shooting you mentioned, it was a very good example where only one narrative existed. There was no comparison here. And so the witnesses were only audio witnesses. There was one visual witness in that file, but it was from across a parking lot through some trees. And she said that she could, tell one was an officer and one was an assailant, and that there was a struggle. That's basically all she saw. So as far as the details were concerned, we were left up to a potentially biased source, which was that of the officer. And so if we're coming in to be an objective party on the investigation, we, just by the nature of the scientific method, we treat that single narrative as the hypothesis, and then we test against it. And if we can't reject it, then we accept it. And this was something, especially using computer modeling, was something that, at least what I'm told, had not been seen in the Ninth Circuit previously. And so upon presenting this to the court, it was deemed admissible and reliable. So we were very happy about that. But it really does make a lot of sense and follow everything that we've been talking about, because through the medical examiner's report, we were able to determine that there were some very specific associated injuries other than the two wound paths. And I think it's important to understand that the two wound paths were very different angles. Okay, we have one coming down at a sharp angle near the navel, smashes through the pelvis, ends up in the buttock. And then the other one, the other round, which we believe was the second round, entered the back of the neck at about C5, C6, transecting the spinal cord, making its way through the heart, and then ending up in the diaphragm. And that round was obviously the lethal round. But from a modeling perspective, it became very useful because at the moment the round transected the spinal cord, there would have been all communication between the brain and the body severed. And we can then now assume that at that moment, the body falls under gravity alone and without muscular assistance. And that becomes very important because a lot of these models are limited. And it's important to understand, pros and cons of everything that you're doing. But for the particular model that we're using, it's just an inertia-based model, so there's no active musculature. So there was some time point in that model that we had to account for that couldn't be explained solely by the acceleration due to gravity. And so what we had to do then is actually create the information based on the narrative the officer gave. And so hopefully I haven't lost anybody here, but basically what we did is we recreated the officer's narrative using video. And then from the video, we could take quantitative measurements. So we could actually, go in there, have everything to scale. We'd know exactly the forward momentum of the subject, the angle of the elbows, the angle of the shoulders, the angle of the torso, et cetera, et cetera, et cetera. And we could use that as input to the model that now acts like musculature activity, right? Because we knew the forward momentum of the person just prior to the first shot. So this is a type of procedure that you go through. And with any modeling exercise, you want to make sure that the inputs are solid, because with any model, it's only as good as your inputs. So if you're using a model, anyone that's listening, please make sure that your inputs are solid. We used a video analysis, but we also used a bunch of ballistics tests. We had a static ballistic test, a dynamic ballistic test. We had a chronographer. findings. We used some findings from the medical examiner. We even used this coefficient of friction between skin and the ground, which you can find in particular databases. And that all went into the input and became very, very important because we knew we had some abrasions. And we didn't know where they were coming from as of yet. And so when we ran the model based on all of this information, it was this movement of a humanoid that kind of lunged forward and then fell to the ground as it got shot 2 times. And so literally the expert on the opposite side said, well, big whoop, you get shot, you fall down. And that was literally quote unquote. And so I said, okay, let's look at this a little bit more and let's take a look at where these contact points actually took place and how much load was actually applied, et cetera, et cetera. So we're looking for that location, direction, and magnitude. And sure enough, I mean, I don't know if your audience knows or not, and Brian, I think we've talked about this before, but if you free fall from about 3 feet, you can fracture your skull, okay? And most people don't even think that if you're standing and you free fall, you can fracture your skull. But in fact, you can, and it doesn't take that much if it in fact is a free fall, and if it in fact is on a very hard surface like concrete, for example, like it was in this case. So it was important to understand that, you know, that we're going from kind of a crouched position, but he was more than 3 feet off the ground, and we didn't see any skull fracture in the list of injuries from the medical examiner. So where was the load being taken up if the second shot that transected the spinal cord actually occurred there? Well, as we watch the model progress, we can see that the knees contact first, taking up some load of the body, decelerating the body as a whole. But because his hands were actually reaching forward towards the officer's primary sidearm, the elbows also took up a large proportion of the load. And so by the time his head hit the ground, it made a lot of sense that all we were seeing was this kind of forward sliding of the forehead on the ground. So the location made a lot of sense because we saw the contact between the forehead and the asphalt in the model. It was a sliding forward motion, which made sense with respect to the forward momentum we had measured in the video analysis. And then there was no fracture present in the sense that we got this load uptake with the knees and the elbows beforehand. And that was something that just, you know, it was one piece of information that we were able to hang our hat on that just blew people's minds. And no one had considered that level of detail before. And it was almost like, you know, there was a struggle. So, of course, there was some abrasions, and that was the end of it. But it was more than that, obviously. You can't hang your hat on just one piece of evidence. There was other abrasions that we could also show contact, location, direction, and magnitude for in the model. But then there was also the shot-to-shot interval. So, and as your audience will likely know, the average shot-to-shot interval for a semi-automatic pistol is anywhere between a quarter of a second and a third of a second. Well, in our model, the timing actually mattered a lot. And in fact, we could only match the wound paths detailed by the medical examiner if we fired the second shot at 276 milliseconds after the first shot. Well, that's bang on in between the average shot-to-shot interval. And not only that, it was consistent with the officer's statements. And now we're starting to get into seeing how, you know, we're now doing all this testing against the narrative, and yet it's all consistent with the narrative. And so if it's consistent with the narrative, we can't reject it. And I'll stop there.
And that's such a great explanation. And it seems to me that there's it's all of these pieces that come together. You talked about, the abrasions, that the knees took up some of that load, and then the elbows. But the piece before that, the understanding of that the spinal cord was transected at a certain point, so the body is falling strictly under gravity. I think anybody that's ever watched fights has seen that the body, a fighter who gets knocked out on their feet, the way that they fall to the ground is very different from somebody who falls to the ground that's still conscious. Was that a key piece, is that you were able to determine when the spinal cord was transected, and so at this point this movement forward was completely as a result of gravity, and so that's consistent when you look at the loads taken up by the knees, the elbows, and then the forehead?
Well, that's the beauty about the modeling program that we use is it actually dictates that movement very, very well. It has every segment of that model is scaled to the size and weight of the deceased. So we were able to scale that model to match the deceased demographic. So his height and weight, basically. And it's based on Newton's three laws. And so if we have the dimensions of the body correct and we have the initial motion correct, then the only other aspect of the model is the acceleration due to gravity. And so, yes, we were very convinced that the motion output of the model was consistent with someone who had a transected spinal cord. Now, does that mean we planned it that way? No, we actually got lucky, and that was the case. We chose the right model for that particular situation. And now we're getting into a whole nother section of this discussion is kind of tools of the trade, and how do you go about choosing the right tool for the job. But the program we used was the right tool for the job because of that particular aspect of the incident.
And you're looking at extreme detail on some of this, like you use synthetic bone ballistic soap in addition to human dynamic testing and human body numerical modeling and these other elements. So you're not just guessing, that as the bullet travels this way or as an impact here, that this is how it will travel through bones and organs?
Hey, Brian, you just dropped out for a second, but I think I got the gist of what you were asking. In this particular file, the model that we're using was a force-sensitive model. And most of your audience will know that in ballistics, it really comes down to two equations, either the conservation of energy or the conservation of momentum. And both of those concepts do not allow you to understand the force applied. And so we couldn't use standard ballistics equations for this. We had to turn to something that was going to make the model more accurate. So we needed to pull a force from this. And so you're absolutely right. We took some ballistic medium and we made sure it was calibrated, obviously. And then we matched the distance that we knew the round traveled through the body before hitting the pelvis, and we knew that from the medical examiner's report. And then we had a pelvis medium called sin bone that kind of matched the thickness of the cortical bone of the pelvis. And lo and behold, once we did all that and shot it, we were able to record the load it takes for a round to move through about 10.5 inches of soft tissue, smash through the pelvis, and then embed itself about a half inch later into the buttock. And it's roughly about 600 pounds, if anyone's curious. The only thing is it doesn't last for very long. And so the actual momentum imparted on the model was relatively low. But we're still glad that we did it because it was an accurate. It increased the accuracy of the model, number one. But number two, we felt that the impact point of the round was at a point in the body that could have affected its movement. So, in other words, it was far enough away from an axis of rotation, if you will. So if you think about a wrench, for example, this was a bullet that was sitting at the far end of the wrench and might have some influence over turning the nut, if you understand that analogy.
Absolutely. And does that understanding then impact your understanding of what position the body would be in when the second shot is fired, to explain why that second shot would have entered not at the front of the body but at the back of the body?
That's what we were thinking initially. And there was a slight change in torso angle between the video assessment and when the second shot was fired. And oddly enough, that was an area of the model that we couldn't account for. And no one asked us about it. And so it kind of gives you an indication that there's not a lot of people that have this expertise and that can ask the right questions. We were up against a very experienced plaintiff lawyer who used to work for the city that we were defending, and so he knew all the ins and outs, and failed to retain an expert that could ask the right questions. And of course, we don't give this information away, but it's something that we have in our back pocket that we'll have to explain if someone asks us about it. And yeah, there was a few degrees of inclination there that we couldn't explain, and it really came down to a few things. Is well, maybe our video quantification of the narrative wasn't exactly correct. That could be one explanation. Another explanation could be that perhaps this individual watched too many cowboys and Indians and understood that even though this wasn't a lethal round, what we believed was the first shot into the abdomen, he understood that, just by intuitively and by watching cartoons, that you go down after a first shot. So that may have influenced his trajectory. It may have been a flinch, because we know that the officer had his semi-automatic pistol out and prepared to fire as this person was lunging toward it. So he could have seen that and been reacting to a potential pull of the trigger. So there's a lot of different explanations for this that we simply weren't asked about. But yeah, you have to be prepared for things like that. And any time you, I suppose, work up a file, you have to sit down with everyone that's familiar with the file and critique it, and make sure that you understand it fully from both the pros and the cons, and be prepared to provide objective answers to any potential hairy questions.
Excellent. Great explanation. I think that's so important that you provide objective information to the court so that the triers of fact can determine make their decision based on that evidence. Now, I want to talk about another case that doesn't involve a shooting. It's a physical force, hands-on by one officer, baton strikes by another. But there was a research project that you did that was conducted with the NYPD on baton strike effectiveness. When I was reading through the case, it sounded like you drew on some of that information in this case. Can you just talk briefly about that baton strike effectiveness study that you did?
Sure. So basically, ASP Incorporated came to us and they said, look, we have a mandate. It's called lighten the load, quote unquote. And they had pulled some information from the UK that showed quite remarkably a connection between ergonomic injuries and the overall weight carried by an officer over the course of their careers. So, and not only that, as the weight got heavier, not only did you increase the number of ergonomic injuries, but you also increased the severity of those same injuries. So the time lost off work, and the lost productivity was enormous. And so ASP Incorporated said, you know what, this is a really good concept, something that we want to incorporate in our products, because we're obviously contributing to the overall weight the officers carrying throughout their careers. And so they recognized that fact. But obviously they didn't want to reduce the effectiveness of any of their tools, specifically their batons. And so they asked us, they said, hey, can you take a look at several baton systems and let us know, what is the effectiveness of our lightest baton? What is the effectiveness of our heaviest baton? And maybe compare it to some other baton systems out there. And so we did that. We had a look at, there was, I don't know if I should say manufacturers actually, because I know that was something that was kept confidential with respect to the report. So I'll hesitate on naming the manufacturers, but just know that they were all expandable batons. Some of them were 24-inch expandable batons. Some of them were 26-inch expandable batons. Some of them were made of different materials, too. There were some aluminum systems there. There were some steel systems, and then there was some very heavy, larger baton systems. And so we just basically categorized these systems into lightweight, medium weight, and heavyweight baton systems. And then we looked at them in two different ways. One was kind of in a very structured lab, controlled environment. But as you know, with everything that you control, pretty soon, this is what science does to look at a manipulated variable. They call it a manipulated variable. So you have to control all other variables, and then you manipulate one variable, is the idea, if you want to understand the effect of it. But of course, as you control all the other variables, you quickly become, you quickly create a sterile environment, if you will, or something that really isn't all that representative of how these tools are used in the real world. So we had a two-step process. We had a more controlled study where we looked at just simply, we looked at EMG of the arm, which is of the electromyography. So we wanted to understand how the muscles were contracting in order to wield the baton. We looked at impact load on a non-moving target as well. And so these are very ideal conditions that officers were swinging at a very fairly large non-moving target, but it allowed us to get very clean, repeatable data. And then what we tried to do is use that clean data and relate it to a more dynamic situation. So then what we did is we gave them a dynamic scenario where we ran them through an obstacle course, if you will. And the first half of the obstacle course was to simply just fatigue the officer and kind of stress them, if you will. We didn't have any flashbangs or smoke or role players or anything like that, but at least we could say through the heart rate monitoring that they were working hard. And so they kind of ran through this obstacle course, making multiple strikes on multiple objects. And then they got to the measurement half of the obstacle course. And so once they were fatigued, we did coordination tests. We did agility tests. We did, I can't remember, there was a bunch of them, accuracy tests on how accurate they were with striking the baton. Also, a dynamic striking load. So how hard could they hit now when they were fatigued and moving dynamically with this thing? And that actually became very interesting because what we found was accuracy, as you might imagine, drops way off. And also the differences in the overall impact load were reduced. So in the controlled experiments, you could see that obviously the heavier batons hit harder. But those differences between the lighter batons and the heavier batons tended to be reduced once you got into a fatigued officer in a dynamic situation. And so that when we were making conclusions for all of this data and information, what we found was that even though the heavier baton did hit the hardest overall, it was rated much lower as far as the usability of it with respect to the officer. So that wouldn't be their go-to baton. Even though it did hit the hardest, they felt it was difficult to use. Their recoil time felt slow. It was heavy. It was fatiguing, et cetera, et cetera. All of these things they were saying that it was an issue. And what we found actually when we took a look at the mechanical properties of the systems was it was really the concept of moment of inertia. And that's an engineering concept that you can simply understand by taking a baton, opening it up, and balancing it on your finger. And the closer your finger is to the impact point, rather than where you're wielding it with your hand, the more effective that baton system. And so essentially what you could do is reduce the overall weight of the baton system as long as you maintain the effective mass closer to the impact point. You would have an effective tool that was now easier to use and overall a lighter weight. And that's kind of the long version of what we found there, but that's really what it boiled down to.
Excellent. Well, and I think it goes to show that, I mean, your research is in so many varied areas, and there's a lot of different examples on your website, but it's not just use of force. So in this case, you're looking at taking all that mechanical and biomechanical information that you have and looking at this particular element. Now, there was a case that you were involved in, and if people are looking at your website, I believe that the article or the research abstract is titled Use of Body-worn Camera Footage in Conjunction with an Injury Biomechanics Investigation Process. And there was a struggle in a hallway with a subject between two officers. One went hands-on, the other used a baton. There was allegations of excessive force afterwards, and the subject was alleging that a number of ongoing medical issues he had were a result of the force used by the officers. So can you talk a little bit about some of the elements, because you brought in research from a variety of areas, including I believe your research on baton strikes in as you looked at this case. Can you talk a little bit about this case?
Sure. Yeah, in the background you gave was correct. I just want to clarify that our job was to understand the event with respect to time course of the strikes, the overall strike load, and the time for the officer to stop once the change in threat had occurred. So that was our task on this particular project. And what we were able to find is because all three officers, there was actually three officers, one didn't get involved. They stood at the doorway. One went hands-on, one deployed their baton. And but what that meant was, well, we had three body-worn cameras from three different angles, which made it very easy to kind of detail this with respect to the number of strikes, the duration it took from kind of wind up to impact, whether it was a forehand, backhand strike, where the location of that strike actually was. And so that's the information that the video gave us was, what was happening, when was the baton deployed, and how many strikes and where these strikes actually landed. Now, we were able to combine that information with our previous research, i.e. the ASP Inc. study, or I should say the ASP Inc. sponsored study. And what we did was we chose the most relatable baton loads from that study to the baton that was being used in the incident. So then we knew, okay, well, this is, at least on average, the loads that we should have seen under ideal conditions. Okay? And then we could compare that to the actual injuries. And this is where it gets really interesting for people because injuries tell you a lot. Even the absence of injuries tells you a lot. And the fact that we weren't getting any fractures kind of puts an upper limit of the loads that the baton could have been applying at the time of contact. But then on the lower end, if we're only receiving a bruise or a laceration, that gives us now a lower bound of the loads. And why do I know that? Because you can turn to literature and figure out for a steel object of this diameter, impacting at a specific velocity, you can now determine the probability or the tolerance of that specific tissue. Okay, so if you're getting a failure of that tissue, you can reason that it's above that specific tolerance level. And so what ends up happening then is you get this window of contact load during the actual incident. Now, here's the interesting thing that happened with that file is there was this inclination or this perception that we were saying that officers should now control their strike force somehow. And that's not really what we were saying. What we were saying is that under ideal conditions, he could have hit much harder. But there's a plethora of reasons why he didn't in the actual incident. One is that we're in a narrow hallway. Impact angle matters. You've got a moving target that matters. Friction between the baton and the target matters. There's just a plethora of things that can affect it. The key is that we understand the event much, much better than if we didn't have that information. And so we combine the ASB-sponsored data with the injury data to come up with a percent effort at contact. And it did not exceed 40% of what the officer could have if the person was like literally still and kind of presenting the target in ideal conditions. And so then from there, we had to determine, well, when was the soonest time the officer could have stopped this intervention, if you will. And we turned to Bill Lewinsky's time to stop studies. And of course, these were, I want to say, simplistic in the sense that it was an audio or visual indicator that simply turned on and turned off. And the officers were asked to shoot as fast as they can and then stop shooting once the visual or auditory indicator had stopped. Okay, so we're talking very clear indication of when to stop. And even under those ideal conditions, you were having times to stop that were exceeding one, or they would go up to 1 to 1.5 seconds. And so in this particular scenario, we argued that it wasn't that clear. And in fact, the only objective indicator that he was complying was he exclaimed, like he yelled, "All right." But as you know, as police officers know, people say a lot of things and do other things all the time. But if we had to look at it objectively from the information that we had, we counted that as the first objectable source of information that could have been interpreted as this person was now complying. And then we just counted out 1 second and 1.5 seconds. And it turns out that the seventh strike, there was 8 strikes in total, the 7th strike fell within the 1 second time frame, but the 8th strike fell within the 1.5 second time frame. So we argued that the officer noticed that the situation was changing and stopped the intervention within a time frame that would have been expected of him. Unfortunately, or fortunately or unfortunately, I don't know, our report was put in the hands of a mediator, and the mediator, based off of not just our report, but other reports and discussions between the opposing attorneys, they came up with a settlement payout of $50,000 for that particular file. And it really kind of rubbed me the wrong way, to be honest, because I felt like the mediator did not understand our report and clearly couldn't have understood our report and the science that was behind it. And so we have a motto around here now that says, if you confuse, you lose. And even though we thought we did a pretty good job of explaining that science, it was a case that we felt really clearly define future goals for us as to we've got to make it even simpler. We've got to make it visual and easy to understand. Otherwise, it's going to confuse, and if we confuse, it's going to lose. Now, I understand that trial is expensive, and that probably played a role as well. That they probably said, well, how much is this case actually worth? And, is it worth it to go to trial, because it's probably going to be much more expensive to try this case than it is to pay it out. I get that. But still, from an engineer's perspective and for our perspective, I felt like the mediator didn't understand, even though we didn't get a chance to talk to him or her. But I felt like the clarity may have been an issue.
And that's a great explanation of the case, and a great explanation of your ability to do an after-action review. And then there's so many factors, like you say, and a lot of times they're looking at the legal fees and say, you know what, it's just way easier, way cheaper. We'll give them money, they'll go away. We're not admitting any fault. And it's bean counter mentality sometimes, which is frustrating for the officers that are involved as well as people like yourself. But to come out with that philosophy of if you confuse, you lose, I think that was a great takeaway. And again, it's and this is the key, is there's people like yourself and some other scientists that I've listened to in other fields that do a very good job of taking the science and explaining in a way that those of us that are not scientists can understand, and that's truly a gift. But I think the key out of this story is that you looked at, you brought together the research on the baton strikes, research on contusions, lacerations, fractures, traumatic brain injuries, research on reaction time, time to start, time to stop, and a number of these factors, and brought it all together to put forward this report. And I think without a complete understanding, it strikes me that without a complete understanding of the biology and the biomechanics and the mechanical engineering, is we're not necessarily going to pull all those areas together or have the ability to pull them together and put it in a format that would make people understand. Is that kind of your experience as well, that you need to, because you're speaking to judges and juries that watch too much television and don't understand the realities of some of these things. They watch, 100 episodes of CSI, and they understand that science is good, but they think it can solve everything in 45 minutes. Is that a key? Is that to continually striving to take all that you do and pull together all of the science, but put it forward in a way that makes it easy for people to understand that don't have the scientific background?
Yeah, Brian, I actually really appreciate that point, actually, because what you said earlier in the question was that there was a number of aspects of the file that we were able to pull on in order to make our conclusions. And that's very, very true, because you're working from the injuries across the spectrum of biomechanics, and then even touching on human factors. And really, they all matter. And so I get it that one person or one outfit can't be all things to all people, but the more aspects you can touch on, the more comprehensive your conclusions are going to be. And so getting those highly experienced, well-educated people with the research background and the boots on the ground experience is where you want to be putting your money. Number one, and number two, the second aspect to that was the ability to take those complex concepts and boil it down to an easy to understand, fundamental view of the event that anyone could understand. And let me tell you, I can't tell you how many times where, the opposite expert is always confrontational, okay? That's kind of the nature of the business. But what I find so interesting, and this goes out to everybody, by the way, not just, police defense people, but is don't talk to the opposite expert. Because if you talk to the opposite expert, you're going to lose the audience that actually matters, which is the judge and the jury. Those are the people you're speaking to. And so, now granted, judges are very astute people, but they're not scientists, they're not engineers. And so you have to take this stuff and make it, in my opinion, as visual as possible. So that's why I think the new technology is so effective at doing this is 3D scans, physical modeling, any software type, photogrammetry, inverse projection photogrammetry. There's all these things, and video analysis. We even did this one analysis where we overlaid the incident video with a thermal image. And you might think, well, why the heck is that? And most people wouldn't think of going there. But what we did was we linked the images that were clear in that low light, blurry incident video with a video where we could actually see the human in every frame. And so it allowed us to link our theory of the incident video to something that everyone could agree on. And that alone made it just a world of difference, because what ended up happening is even on the team meetings that we had via Zoom, when we're looking at this video, we had 5 different experts. They had 5 different opinions on what was happening in each frame. And so you can imagine what's going to happen once an opposite side of the bench team gets at it. And so, the more that you can explain things very simply, even though that was highly technical, it was a very visual way to explain our theory of the movement that we thought was happening in the incident video. And so that stuff, just blew people's minds, and it becomes, it solidifies your theory very, very well. And they don't even have to get into the nitty-gritty engineering, physics of your report or the appendix of your report, because you've served it on a silver platter that everyone can see and understand.
Excellent. And it reminds me of a quote that I heard from Dr. Andrew Huberman, a professor of neuroscience at Stanford, in a webinar or podcast that he was doing, where he talked about the philosophy: assume zero knowledge but infinite intelligence. So speaking a way that people, you assume that they have no knowledge, but they have an infinite intelligence, the ability to understand it if you explain it simply, which is, you have a great ability to do that. So talk about your website, how people find out more about the services that you offer, because you offer a number, in addition to the consulting work that you offer a number of training programs. So talk about how people find out more about GTD Scientific and everything that you offer through your company.
Sure. A lot of our published research is located on our website, the About Us page, what is the science of violence, et cetera, et cetera. They're more general descriptions, but a website is a good place to start, and that's at gtdscientific.com. So just Golf Tango Delta Scientific.com. Good place to start if you want general information. If you want more specific information, just feel free to contact us. Everyone gets 30 minutes. My phone number, I know this is a closed, is this a public forum, Brian,
No.
that this audio recording will go to?
No, it's members only, and they're all law enforcement trainers.
Okay, perfect. So my phone number is 604-842-4831. I'll just repeat that, 604-842-4831. Feel free to call me anytime, and I'll be happy to give you 30 minutes. Or you can email us at admin@gtdscientific.com. That's admin@golftangodeltascientific.com is another good way to get a hold of us. And we'd be happy to field any questions or let you know if we can help you with that file.
Excellent. And I would encourage people to go and spend some time on the website and click around. There's a lot of great articles. There's articles and some research abstracts that go into more detail about the cases that we talked about. So, Jeff, I want to thank you for your time today. I know you're a very busy man. I know you got another interview right after this, but I want to thank you, more importantly, for all your service starting back with the Calgary Highlanders and your service with the Canmore Emergency Services, and then your service in bringing the world of science to help us understand the dynamics of some of these events and fill in some of those gaps that have been there for us historically in these investigations and in our understanding. So for everything that you have done, everything that you continue to do, thank you so much for that service.
Happy to help, Brian. Thank you so much for having me on the show.
It was certainly my pleasure. And so for the members of the Excellence in Training Academy community, as always, I encourage you to let the information that Jeff shared. He shared a lot of great information. Let that information simmer, percolate overnight, and then be intentional about sitting down tomorrow, writing out your takeaways, writing out your action steps. And as I said, one of the first action steps I think you should take is to go to the website and read some of the research abstracts and some of the articles to get a deeper understanding. So to the members of the Excellence in Training Academy community, thank you as always for your commitment to excellence both in and through training. Always continue to train hard, train smart, train with passion and purpose, and always be willing to dare to be great.